Now we're going to go ahead and discuss concavity. And concavity is talking about how a function curves as it's increasing or decreasing. And so what's really important to remember here is we're looking at, instead of looking at a function increasing and decreasing, we're looking at its derivative. So as I'm moving from left to right on the function x cubed, right here there's my tangent. But as I move over from the left to the right, what I can see is that the slope of my tangents, f prime, is decreasing. This is what we call concave down. If I continue going, what I eventually start to notice is that here, continuing moving from left to right, as I go and I start looking at other tangents, I'm noticing now that the slopes of my tangents are starting to increase. So another name for slope of tangent is derivative, is increasing. This is what we call concave up. Now note that my function x cubed is increasing the entire time. We were not talking about the function increasing. We were looking at the slope of the function, in other words, it's the derivative. So over here on the left side, our slope was decreasing, so it's concave down. Over to the right, slope is increasing, and that is concave up. We can use initials. Concave up is CCU. Concave down is CCD. Kind of non-formal terms that I use is concave down is frowny face, concave up is smiley face. It's kind of describing the curves that they're making. Now the way we can decide if f prime is decreasing is the same way we decide if a function is decreasing. F prime is decreasing if its slope is negative. Well, the slope of f prime is f double prime, and if that is negative, it will be concave down. So the way I can tell concave up is looking at the slope. We're saying that f prime is increasing, which means its slope, f double prime, would be positive. So the formal definition of concave up and concave down is talking about f prime increasing and decreasing. The way we decide if they're increasing or decreasing is looking at second derivatives. And so here we have kind of our formal definition here. So the graph of a differentiable function f is concave up when f prime is increasing, and concave down when f prime is decreasing. And then in parentheses here, mathematically, how we can actually find that. So if I continue looking at x cubed, kind of doing this algebraically, if I want to determine the concavity, what I need to look at is the second derivative. So first thing is I need the first derivative, which would be 3x squared. And this is what I use to find increasing and decreasing. But to find concavity, I need its slope, which is the second derivative, which is 6x. And from here, I actually follow exactly what we did with first derivative in our first derivative test. I want to know where is my second derivative 0, and where is my second derivative undefined. Well, undefined is the easier one here in that 6x is never undefined. And then where 6x is equal to 0 is x equals 0. And so these are like critical points. We don't call them critical points, but that's how we find them. And I can use a sign chart for this as well. Domain of x cubed is all real numbers, so there are no endpoints. The only point I found here where the second derivative is 0 or undefined is 0. And this is for my second derivative. So if I pick something less than 0, like -1, and plug it into the second derivative, I get a negative, which would mean concave down. If I pick something bigger than 1, like 1, and bigger than 0, like 1, and plug it into the second derivative, I get a positive, which would mean concave up. So my function is concave up for x is greater than 0, and concave down for x is less than 0. A point of inflection is related to this. This is where the graph of f has a tangent and that is key, is it must have a tangent there and where concavity changes. So, for example, if I go and we're looking at the x cubed function again, I know that a tangent exists at x equals 0 because x cubed is differentiable everywhere. And so I can find the first derivative there. And the second part of this is we saw on the previous panel here that at x equals 0, concavity changes. And it's not just that where x equals 0, the concavity must change from up to down or vice versa at this point. So x equals 0 is a point of inflection. And that's because tangent exists there. In other words, the first derivative exists there, and the concavity changed.